I'm Jaesoo from Chungbuk National University, Korea. In this talk, I'm going to present path-based subgraph searching in distributed environments. The table of contents is as follows. A graph represents multiple relationships between objects in social media, biological networks, and IoT. Recently, large amounts of graphs have been generated in social media, IoT, and so on. Distributed processing techniques have been proposed to effectively process large amounts of graph big data. In distributed graph processing, subgraph queries are frequently used in various applications that use large graphs to determine which subgraph matches a certain pattern. Subgraph query processing requires performing a subgraph isomorphism test to identify a graph that structurally matches the query in all graphs. The subgraph isomorphism test compares all possible subgraphs in a large graph and is therefore NP-complete. To solve NP-complete problems occurring in subgraph query processing, filter then verify and pass query have been proposed. In filter then verify, called FTV, and an index by extracting features of subgraphs is required. A candidate set matches the features of the query is extracted through the constructed index. But a subgraph isomorphism test is performed for the extracted candidate set to verify whether they actually match the query. The past query method searches subgraphs without executing a subgraph isomorphism test algorithm. Starting from a vertex in the graph that matches the query, all paths are searched for the connected neighbor vertices to check whether they match the vertex of the query. However, the existing path query methods have no special criteria for selecting the start vertex and don't take the cost model that can reduce the processing cost. In this paper, we propose a distributed path subgraph query processing method to search a subgraph with the same label as the query in Spark. We calculate the filtering score to search for the subgraph that matches the query with a smaller number of searches. The proposed method has three contributions. First, we predict the filtering score to avoid the vertices that do not need to be searched based on the statistical information of the graph. Second, we determine the search order that determines the priority of the vertices to be searched among the vertices of the query through the filtering score. Finally, we partition the query into sub-queries according to the filtering score for distributed query processing in Spark. In the path query method, searching for a certain vertex can have a significant impact on the search to minimize candidate results that satisfy partial query condition. If there are countless starting vertices that are searched first, numerous parallel searches are performed and then lead to a larger number of unnecessary searches than the number of vertices actually required for the search. So the proposed method calculates the filtering score to search for the subgraph that matches the query with a smaller number of searches while reducing the unnecessary searches. A vertex having a high filtering score is a filter more necessary search. If the search is performed in the search order of the vertices from the highest to the lowest score, the search time can be reduced further. This figure is the overall processing architecture of the proposed subgraph query processing method. In the distributed environments, the graph is distributed according to the pattern policy and stored in multiple slave nodes, and the statistics are collected for the entire graph. As the search order has a significant impact on the performance in past query, we compute a filtering score to determine search order for query processing. The filtering score is calculated based on the statistical information to reduce unnecessary search. The query is partitioned into triplets according to the filtering score to perform parallel searches. The parallel searches are performed at each slave node in Spark according to the determined search order. The search results are transmitted for the joining through communication between slave nodes, and results are finally joined at one slave node. The proposed method defines a filtering score to determine the search order for query processing. The filtering score is the filtering probability calculated through the probability density function. The filtering probability considers three probability density functions. Normal Fs calculates through the probability density function of the normal distribution. Power Fs calculates through the probability density function of a power law distribution. ABG-DGFS calculates using the average degree of a particular label without considering the probabilistic distribution of the data. Normal FS is calculated by equation 1, where G all is the total number of vertices in graph G, GL is the number of vertices with label L in graph G, and FPND Vi is the filtering probability of normal distribution. Power FS and ABG-DGFS are calculated by equation 2 and 3 respectively, where FPPD-Vi is the filtering probability of power law distribution, ADL-Vi is the degree of collected labels. A vertex that has highest filtering score among the vertices of the query is selected as the starting vertex, and the query is partitioned into triplets comprising a vertex having the next highest filtering score among the neighbor vertices connected to the starting vertex. The query partitioning is performed for all neighbor vertices connected to the starting vertex. When the partitioning with the neighbor vertices is finished, the same operation is performed at the vertex having the next highest filtering score among the vertices connected to the neighbor vertices of the starting vertex. The master node instructs each slave node to perform the query according to the search order. The slave nodes that have received the instruction perform the search in their own partitions and record the result in the result table. When the searches of all rounds finish, the list of the vertices recorded in the result table by the slaves become the subgraphs of the initial query. This figure is the search results by round. As a result of performing R1, V1 connected to V3 is searched, but the graph has no vertex with a label A connect to V3, V1 in R2. Therefore, the H V3, V1 is excluded in the results of R2. As it has been removed in R3, there's no need to search for the vertices with a label D connected to V1. The join tag is used when sending or receiving the result between the slave nodes after local search. In R2, a replicated V4 was obtained and the join tag was marked. As a vertex with the join tag indicates there is a path in another partition, the search begins again at the vertex with the join tag in R3, which is the next round. This figure is the result of the search result joins. When the partition query searches are finished, an intermediate search result table is created in each partition. And the intermediate result tables are sent, received using communication between the partitions for the join. The partitions that have finished searching already and are in the waiting state send their intermediate result tables if there is a next partition that has finished the search. The partition that has received the intermediate result performs the join with its own intermediate result table. To show the superiority of the scheme, we perform performance comparison with the existing schemes. To perform the experimental evaluations in a discrete environment, we constructed 3 Spark-based clusters and implemented them through Scala in GraphX. And we used the real data sets provided by Stanford. This table is a data set used in the performance evaluation. This figure is the search time according to the data sets. Although the difference in the performance was not noticeable compared to the existing method for small data set such as Sunny Dip, the difference was large in the search time as the size of the graph increased. This confirms that the search order determination method proposed herein is significant. Furthermore, the time required for determining the search order by calculating fs through the collected statistical information and partitioning the query was not long compared to the search time. This figure shows the search time among query types in real dataset. Query Q1 shows almost no difference in the performance. A simple query Q1 did not show a large difference in the performance evaluation of the real dataset. Significant performance differences were observed in Q2, Q4. In Q4, the most noticeable performance difference was shown in the comparison of the existing method. The proposed method shows strengths in queries of mixed structure, such as Q4, because the search method of the past that can create the query with a small number of searches is predicted by predicting the probability of each vertex occurring in the graph for the query, rather than random searching. In this paper, we propose a path-based graph query processing method to search subgraph in Spark. The filtering score is calculated to eliminate unnecessary searches in the query search through the distribution of the vertices of the graph and their edges. Based on the calculated filtering score, the vertex that can be filtered most is selected as the starting vertex, and the search is performed by the partitioning the query into subqueries of a smaller units depending on the filtering score. In near future works, we will further improve the performance of the proposed method and expand it to be applicable to various distributed environments. In addition, we will conduct experimental evaluations with the recent studies using various datasets. Thank you for listening to my presentation. If you have any questions, please do not hesitate to contact me via this email.